Hello, my name is Paul Galatic, and in this video I will be discussing neural style transfer for video and how it can be performed with distributed computation. First, I'll explain the neural style transfer or NST problem and how it applies to video, along with currently available methods. There is already an algorithm to perform neural video stylization, yet a new approach is necessary. Because right now, stylizing a video can take hours or days on most computer setups, even for relatively short videos. I'll then go over the nature of the algorithm I developed and what goals I had in mind when I programmed it. After that, I'll discuss how my algorithm measured up against the goals I set for it. Finally, I'll discuss what I learned during development, and also I'll discuss promising ideas for future research in this area. So what is neural style transfer? It is a domain adaptation problem. We take an input image and a style image and combine them such that the major features of the input image are preserved while the texture appears repainted in the appearance of the style image. The program I used to create these samples can be found in the video description. Every NST algorithm has a slightly different stylization method. Some trade speed for quality, others flexibility for speed, and so on. I will cover the specifics of NST in a bit. First, let's compare and contrast algorithms that already exist. I'm going to assume the viewer has some familiarity with convolutional neural networks. The seminal algorithm that introduced NST is A Neural Algorithm of Artistic Style by Ghiasi et al. Their network begins with an image of random noise and shapes it so that it exhibits both the stylistic aspects of the style image and the major features of the input image. They measure how well the network performs at this task by introducing the content and style loss functions. For now, consider the content loss to be a measure of how well the output image reproduces the major features of the content image, and consider the style loss to be a measure of how well the output image reflects the essence of the style image. Because the optimization process happens on an image-by-image basis, this algorithm has a very low throughput. The next algorithm, by Johnson et al., trains networks to minimize perceptual loss. Perceptual loss compares high-level features between images rather than granular details, and so is much more in tune with the priorities of NST. That said, the primary difference between this method and the previous method by Ghiasi et al. Is in how Johnson et al. Structures the loss function so that a neural network can learn to apply a specific style to an arbitrary input image. Such a network, once trained, stylizes images with a feed-forward process, and so can produce output 1,000 times faster than Ghiasi et al. However, these networks are limited in that they can only apply one specific style to an arbitrary content image. In order to learn another style, an entirely new network must be trained. A reasonable person may consider the NST for video problem solved with the introduction of Johnson et al. Say that I wanted to stylize a video. This is my go-to input video. The standard naive algorithm for stylizing video is to simply take every frame of the video and stylize it as you would an image. These stylized frames can then be recombined to produce a video. This approach is fast and simple, but introduces undesirable flickering artifacts, as you can see here. Notice how the background seems to twitch wildly, creating the illusion of movement. We can do better than this. Reuter et al. Created the algorithm Fast Artistic Videos, or FAV, with a combination of the loss from Johnson et al. And their own novel constraints. This network is given the current input image along with two additional images that help preserve consistency between the stylized frames of the video. This approach produces stylized frames with a feed-forward process, which is very fast with a good setup, i.e. with GPU acceleration. Here is the video from before, stylized with FAV. As you can see, the background shimmers and blends around the floating dog head rather than flickering. So, why create a new algorithm if we already have FAV? The reason has to do with the current state of FAV and its dependencies. FAV was written in Torch 7, an open source Lua library based on the Torch deep learning framework. After FAV was published, several users reported that their FAV installations were generating improperly stylized videos that bore no resemblance to either the original video or the style that was supposed to be applied. I observed the same effect when I tried to implement FAV. This is most likely due to an interaction between a Torch 7 library and one of the libraries that enable GPU acceleration, CUDA or cuDNN. Because FAV has exited active development, there is little hope of this issue being definitively fixed. Before we can discuss NST for video, we must understand NST for images. I'm going to lay out some terms. XI refers to a given frame at position I of the input video sequence. YI refers to the stylized frame at position I of the output video sequence, and S refers to the style image the network was trained to apply. NST forms the basis of its operation on a mathematical interpretation of artistic style. Two objectives present in every NST algorithm are to minimize the content loss and the style loss. Both losses depend on a pre-trained VGG network. VGG is designed to have good performance on a benchmark dataset called ImageNet, but its final predictions are useless for NST. In order to make predictions though, VGG must first extract features from images. NST algorithms use this feature extraction process as a basis for the content and style losses. By doing this, the exact pixel-by-pixel details of XI and YI are less important than the features that VGG, and in some sense that humans, can see. Content loss measures how well the network preserves the high-level features of XI in YI, for example, the edges and corners. Theoretically, several VGG layers can be used to calculate the content loss. In practice, though, only one layer is commonly used. FAV uses the layer of VGG16 called ReLU33. It runs XI and YI through VGG16 and extracts features from ReLU33 for the purposes of comparison. Here is the equation for content loss, where L of X is the post-activation features of layer L of VGG16, in this case ReLU33, given an input X, and where magnitude L is the size of the layer, i.e. the product of its dimensions. It's simply the mean squared error between the features that VGG extracted from the input image and the features that VGG extracted from the output image. Style loss measures how well the network applies patterns and colors from S to a given output Y. This is done by measuring the MSE between the gram matrices of L of S and L of Y. In measuring the difference between the gram matrices of L of Y and L of S, we reward the network for reproducing the same pattern of features in Y that are in S, and avoid penalizing it for not reproducing those effects in exactly the same places or exactly the same shapes. Here is the definition of the gram matrix calculation used in FAV, where L is a layer of VGG, L of X is a post-activation feature matrix flattened into two dimensions, and magnitude L of X is its size, i.e. the product of its dimensions. X is used here because we calculate the gram matrix of both Y and S. Here is the definition of style loss. Different from content loss, this time FAV uses several layers of VGG16, ReLU12, ReLU22, ReLU33, and ReLU43. The perceptual loss used by Johnson et al. Is simply a weighted sum of the content and style losses. The weights alpha and beta are chosen by the user. These constraints are all that are required to stylize images. You can use these functions to optimize an image in Gaddis et al. Or to train a network in Johnson et al. However, as we saw earlier, in order to stylize a video, we must accommodate further constraints. To stylize X0 and create Y0, FAV is equivalent to Johnson et al. The first frame of a video is stylized independent of the rest of the sequence because no prior information exists. For all subsequent frames, we must recreate the same pattern of stylization in YI that was in YI-1. This means keeping the brush strokes, the blobs of color, and the shading the same in both frames. One way to do this is to incorporate the optical flow of objects in the video. Optical flow is an estimate of how pixels move between two images. Generally, these images are adjacent frames of a video. FAV relies on dense, accurate optical flow files that describe the motion of every pixel between every xi-1 and xi. Let Fi be the forward optical flow estimating how xi-1 could become xi, and let Bi be the backwards optical flow estimating how xi could have come from xi-1. Optical flow is only useful if it is accurate, and even the best flow computing algorithms stumble when objects emerge from behind others, occlude others, or exit the frame, among other scenarios. In order to account for these, FAV computes a consistency check Ci between Fi and Bi by applying a method for detecting occlusions and motion boundaries that was originally described by Sundaram et al. In areas where their estimates are valid, Fi is roughly the opposite of Bi. Large disagreements between the flow files denote areas of inaccuracy that must be restylized. Now that the consistency checks are available, we can define temporal loss. In this equation, sequential order is important, and so we include the index I of each file and abstract the mean squared error into its own function. The circle with the dot inside denotes the Hadamard, or element-wise, product. This leads us to the final loss formula, video loss, which is a weighted sum of the previous loss functions. The perceptual loss is expanded here for the sake of clarity. Alpha, beta, and gamma are weights chosen by the user. This loss function is used as part of the training process of FAV. Let's look now at the architecture of the model used by FAV. It looks intimidating, so I'll break it down into pieces. First, let's look at the input tensor. It looks like one blob of data, but in reality it's 3 different images. 2 blue-green-red images, and 1 grayscale image. I'll explain how to calculate those a bit later. The first 3 convolutional layers expand the number of channels from 7 to 32, 32 to 64, and lastly, 64 to 128. The process of convolution encodes the input frame into abstract feature space. Once the data is in its expanded state, it goes through 5 residual blocks. The residual blocks are responsible for performing the stylistic adjustments in feature space and allow the network to learn a residual mapping between the input and the desirable stylized output according to the objective functions. This is an application of the Resnick technique introduced by He et al. More specifically, it follows the residual architecture originally described by Gross et al. After that, the data's non-channel dimensions are scaled to double their original size, and its channels are reduced from 128 to 64 by a deconvolutional layer. After more upscaling, the channels are finally reduced to 3. The process of deconvolution is, in this context, similar to decoding from the abstract feature space back to image space. The final output is multiplied by 150 before being returned. The final layer in the network is called total variation, or TV. It is used to regularize FAV and is included here for completeness, but has no function outside training. Let's discuss the preprocessing required to provide input to FAV's neural network. Here's a diagram that describes the procedure. I'll go over it step by step. First, preprocess xi to produce x'I. Preprocessing is converting the image to a torch tensor and subtracting the VGG mean, a special constant. Then erode Ci according to a min-pooling operation, producing C'I. Next, warp yi-1 according to Bi and apply the same preprocessing as the first step to produce y'-i-1. Mask this with C'I to form y''i-1. Concatenate the products of the previous operations into a tensor. If we're stylizing the first frame of a video, y''i-1 and C'I are substituted with equivalently shaped 0 tensors. This is the tensor that is ran through the network to produce the output, which is then deprocessed which is the inverse of preprocessing, to produce the stylized output. So, what gains can we make by distributing the work of FAV across a computing cluster? As we can see, the optical flow inputs required for every pair of frames depend only on the input frames. As a result, these files can be computed independently of each other, and so the work of creating them can be evenly distributed across a computing cluster. However, we can also see that stylizing a given frame requires already having access to the stylized output of the previous frame. This seems to preclude distributing stylization. FAV has the implicit assumption that all adjacent frames are related to each other, which is not actually always true. Many videos have cuts, i.e., a form of scene transition where two adjacent frames carry no important information between them. These cuts allow the video to be split into sub-videos that can be stylized independently of one another, and later reassembled with no loss of visual fidelity. Thus, videos that have cuts can benefit from even further distribution of labor. My algorithm is called Distributed Artistic Videos, or DAV. It's based on PyTorch, which is one of the most popular current deep learning platforms, instead of Torch 7. I didn't train any new models for DAV. Instead, I converted the models created by FAV from Torch 7 to PyTorch. As we'll see later, just converting to PyTorch improved the speed of the algorithm considerably. Here is a diagram of the process DAV uses to distribute video stylization. Again, it may look complex at first, but I'll break it down to make it easier to understand. Before I do, it's important to note that DAV assumes all computers in a cluster share a file system. DAV uses this shared directory to store placeholder files that denote which tasks have been claimed by which computers. DAV has 4 phases. The first and the last are serial components that cannot be effectively distributed, yet because they are so fast, the impact they have on computation time is insignificant. The 2 in the middle are slow, but can be distributed to great effect. First, one node splits the video into a collection of frames, storing them in the common directory. This phase also calculates the partitions used in phase 3. Partitions are sub-videos defined by the cuts in the original video. Cuts are identified manually to ensure their accuracy. Phase 2 calculates optical flow. This process is organized in the form of tasks, where a task denotes computing the 3 optical flow files between a pair of consecutive frames. Once a task is claimed, the node that claimed it will compute the optical flow between a pair of adjacent frames, forward and backwards, and the consistency check, placing all 3 resulting files in the shared directory. After the pre-computation of optical flow is finished, computers stylize sub-videos in phase 3. They claim sub-videos the same way they claimed optical flow tasks. The stylized output frames are then moved to the common directory. In phase 4, after the stylized output is computed, one node combines the frames into the final stylized video, placing the final stylized video into the common directory. So, how do we compare FAV and DAV? Well, DAV must demonstrate 2 qualities. The first is functional equivalence to FAV, measured based on the original loss function from Reuter et al. Functional equivalence means that both algorithms produce outputs equivalent in quality, rather than outputs that are exactly identical. The second quality DAV must demonstrate is a massive speedup when run on multiple computers compared to FAV. Evaluation was performed by stylizing videos with FAV on one computer and DAV on several differently sized clusters, sampling different inputs and styles. I measured how the stylized output videos compare to each other in terms of quality, measured qualitatively and quantitatively, and how long they took to produce. Videos are naturally heterogeneous, having different lengths, resolutions, and numbers of cuts. The dataset I used has 30 videos, each of 720p resolution. They range from short vines featuring scenes in real life, hundreds of frames, to video game and movie trailers in high fantasy settings, thousands of frames. These videos are used because they best approximate the most likely use case for DAV in the near term, people stylizing short videos for fun. Here are some examples of frames generated by FAV and DAV. As you can see, they both produce nearly identical output even across different models and inputs. Here is also an example video stylized by FAV on the left and DAV on the right. While they have some differences, they are equivalent in quality. Here is a table of the losses generated by FAV and DAV across different inputs. At times, FAV slightly outperforms DAV, and at times DAV slightly outperforms FAV. Because the loss function has a range up into the millions for an uninitialized network, a difference in loss of a few thousand is inconsequential, which is why I normalized the total loss by 10 to the 6th. Here is a table of the total average losses for FAV and DAV. These slight variations are acceptable and demonstrate that FAV and DAV produce the same output. So, now that we know that they're functionally equivalent, how do they compare in terms of performance? Here is a graph of the speed of FAV versus DAV run on various clusters. DAV-N stands for DAV ran on N computers. DAV1 means DAV ran on one computer, DAV2 means DAV ran on 2 computers, and so on. The y-axis is the average SF, or the seconds per frame to stylize a video. That is to say, the number of seconds it took to stylize a video divided by the number of frames in that video, averaged across all runs of that type. On top of each bar after the first will be 2 numbers. The first compares the speedup of that bar to FAV, and the second compares the speedup of that bar to the previous bar. FAV performed the worst, taking about 28.2 seconds per frame to stylize a video. Just by converting from Torch 7 to PyTorch without any distributed computation, DAV1 cut that time by 56.5%. It takes DAV1 about 12.3 seconds per frame to stylize a video. DAV2 cuts that time nearly in half, stylizing videos in about 7.1 seconds per frame. DAV4 cuts that time in half yet again, stylizing videos in about 3.1 seconds per frame. Finally, DAV8 yields further speedup, stylizing videos at about 2.2 seconds per frame, or 92.1% less than FAV. As you can see, there appears to be a diminishing returns effect between DAV4 and DAV8. Here's the same graph, but instead of looking at the overall dataset, we're only considering speedup over the subset of videos that have no cuts. As you can see, there are still significant gains, but the diminishing returns effect is more apparent here. Here's a graph that measures speedup only over optical flow calculations, ignoring stylization. FAV isn't included here because FAV computes its optical flow files concurrently with its stylization, and so it is difficult to measure how long stylization or optical flow take independently of each other. As you can see from the graph, the speedup is almost linear, which makes sense as the work of optical flow is evenly divided between computers. Stylization is a different story. On average, for the dataset I used, the actual time spent performing stylization after optical flow was calculated was virtually identical between DAV4 and DAV8. This is the source of the diminishing returns effect. It's even easier to see when looking at stylizing the subset of videos that have no cuts. By definition, these should take the same amount of time to stylize regardless of the cluster size I used. However, I ran my experiment on Cloud Lab, and I believe I was inadvertently provided with more powerful machines for some experiments than for others, regardless of what I had requested. Even on videos that had many cuts though, DAV4 performs similarly to DAV8. This is probably due to a lack of load balancing or other efficiency issues in the initial implementation of DAV, which have since been corrected. Here's an example of a video stylized with DAV8. It would have taken FAV over 17 hours to stylize this video given the same hardware and software. DAV8 stylized it in 1 hour and 1 minute.
Is that music?
It's a good choice.
Hey, well played.
We got no ship. No crew. How are we gonna get out of this one?
We will find hope in the impossible.
promise I won't die alone. Well, that's just typical. Let's hope this doesn't get messy.
This is where it begins, Captain. This is where the frontier pushes back.
What the hell is this?
I know why you're here. Why we are all here.
Okay, let's never do that again.
Let's talk about potential improvements to DAV and directions for future research. When DAV was first implemented, it generated an enormous amount of intermediary files at runtime. Not only is writing these files to disk a source of slowdown, but storing them can be challenging in and of itself. A 2-minute long high-resolution video can generate over 100 gigabytes of data. This flaw drastically limited the scalability of DAV. After testing concluded, DAV was adjusted so that optical flow jobs are allocated from within the stylization procedure. That way, optical flow files are consumed, i.e. deleted, after they are processed by the network, sharply reducing the likelihood of overutilizing disk space. Another flaw in the original implementation of DAV is how partitions were allocated in the order that they appeared. On edge cases, where a video ended with a particularly long partition, DAV always allocated that partition last, which caused a long period at the end of Phase 3 where only one computer was working. All other concerns equal, the most effective load balancing strategy for DAV is to allocate the largest partitions first. DAV now behaves in this way. Originally, DAV was designed to place the files it produced in local directories and only move them to the common directory when absolutely necessary. Since the testing environment used fast LAN connections, this somewhat overbearing strategy was unnecessary for the purpose of evaluating DAV, and so it was scrapped. Because of this, DAV relies on quick access to the common directory to perform well. A slow connection will strangle its throughput. GPUs were avoided for this work, both for reasons of practical necessity and because GPUs are not required to demonstrate how effectively the work of stylization can be distributed across a cluster. This said, GPU-accelerated computers could be easily integrated into DAV alongside CPU-only computers. Now that DAV is based on PyTorch, updating it to support GPU acceleration will be a simple endeavor. As for future work, while style transfer algorithms have long relied on pre-trained networks that can apply only one specific style, new works have introduced NST algorithms that can successfully apply style inputs that they have never seen before. This has obvious implications in NST for video. The ability to apply an arbitrary style would greatly benefit the flexibility of neural video stylization. An alternative avenue of research worth pursuing is designing a meta-network that can create lightweight video stylization networks using an approach similar to Shlens et al. This approach would benefit low-power devices in particular, for example mobile phones or tablets, because the models produced by Shlens et al. Are simple and lightweight. Now to wrap everything up. Distributed artistic videos is functionally equivalent to its predecessor, fast artistic videos. The neural inference of the original Torch 7 model is completely translated to PyTorch and can be distributed with no loss in artistic quality of the videos it produces. Basing the architecture on PyTorch instead of Torch 7 gave DAV an initial speed boost of 56.5%. Distributing the work of optical flow and stylization across a collection of computers allowed even further speed up. Across 8 computers, the time taken to stylize a video was reduced by an average of 92.1%, pushing stylization time from a scale of hours to a scale of minutes, and bringing into possibility the stylization of long, high-resolution videos that were previously intractable to process. A link to the GitHub repository containing my code, as well as sources for the various papers I referenced, are in the description below. Thank you for watching, and have a good day.